Okay. Just a little bit to the side so that you see the slides. All right. So last week we were basically talking the entire time about Pearson's correlation. And we have also learned, so as you may remember, that there are certain assumptions that have to be met. So for inference tests on Pearson's correlation coefficient, so that means if we want to determine whether so a certain sample comes from a population, which is a correlation, the true correlation is, well, let's say 0 or has some specified value. So, and then we can do two things. So if the correlation, so if the assumed population parameter, so the assumed correlation as a population is different from 0, then we do these R to Z transformation, right? So we use a method that has been developed by Fisher to convert our statistic into a different score. And this score, so the advantage of this transformation is that this new score is approximately normally distributed, so follows a Z, basically, right? So it's like a Z score. And so that allows us to use the standard normal distribution to test our hypothesis. So if our assumed, basically if we're testing the assumption whether our sample comes from a population with a true correlation coefficient is 0, which is in most cases true, so mostly we're interested whether the correlation is significantly different from 0, then we can use a slightly easier and less susceptible method, so we can basically use a test statistic that follows a t-distribution. So right, but so the important thing to remember is that in both cases we assume that the data follow a bivariate normal distribution. Yeah, so that we have so that each variable in itself is normally distributed, and then that for each basically value of one variable, so the conditional distribution of the other variable is normal as well, right, and has the same variance. So and that is not always given, right? So we often have skewed distributions, we often have outliers, which are a problem, and we have discussed how so inferences that are based on either the R to Z transformation or the T distribution are susceptible to those deviations and can lead to conclusions that are not appropriate, right? So we can assume that there's a correlation where there's actually none, right? Or in some cases, but that is more related to outliers. So we might also have cases where a true correlation is masked. Okay, so so what can we do, right? What can we do when so our assumptions are not met, right? So if our data are not, for example, not normally distributed or not do not follow bivariate normal distribution. So one option is to use correlation coefficients that have been developed actually for ordinal data. So that means data that are not on an interval scale, but at least on an ordinal scale. So basically ranked data. So everything that can, where order is a meaningful information, right? So everything that I can bring in a rank order. And so the advantage of so these correlation coefficients is that they do not assume, that they make not any assumptions about the distribution of the underlying variables. So they're distribution free, so also non-parametric. So that means there are basically two situations where it's appropriate to use those different correlation coefficients, right? Either that the scale of our data is not sufficient for Pearson correlations. That means we don't have at least interval scale, or so we have an issue with the normality assumption or issues with outliers, right? So outliers are a little bit more differentiated topic because so non-parametric correlation coefficients are not as sensitive to outliers as Pearson's correlation, but it does not mean that outliers are no problem at all. It's just less of a problem. Okay, so in the first coefficient, that we could use as an alternative to Pearson's R is Spearman's rho. And Spearman's rho is basically, so from a mathematical point of view, very similar to Pearson's R. So it's calculated based on the same formula. The only difference is that basically, so we calculate Spearman's rho on the ranks, not on the actual values, right? So if you have a data set and you assume or you suspect that the data is not normally distributed, or that the bivariate normality is not given. So then basically what Spearman's rho does, it just calculates Pearson correlation coefficient on the ranks. Yeah, so you don't have like, yeah, I don't know what, right? So if you wanted to correlate weight and height, so you wouldn't have like measures in pounds and inches for each participant anymore, but you would have rank order, right? So one participant then would be rank 2 on height and rank, I don't know what, 5 on weight. Yeah, and you would basically, as I said, to calculate the Pearson correlation on these two rank orders, right? So for your basically the variables, so the values would now be the ranks. Okay. So typical examples, right, where you have data that are so naturally, so not on an interval scale, is if so you have like you have some competition, right? And so somebody is like first place, second place, third place, fourth place, and so on, right? So that's typical ordinal scale. Or if you have letter grades, right? So that is also an A plus minus, B plus minus, C plus minus, D plus minus, F. So that would also be an ordinal scale. So those are examples where we want to use Spearman's rho. I don't know why my my cursor always doesn't work with the full presentation slideshow. Okay, so one important thing, let me just move that a little bit here away so I can't see you anymore now, but so you can see the full screen. So an important thing is that comes due to the fact that we are transforming the scores into ranks, is that so the way, basically the nature of the relationship that we actually measure is different, right? So remember that Pearson correlation measures a linear relationship. So that means a relationship that can be represented by a straight line, yeah, by a linear function. So I express, right, so one variable is a linear function of the other variable. We will talk about that in more detail tomorrow when we talk about regression. So Spearman's rho, on the other hand, is not a measure of a linear relationship as such, but it's a measure of a monotonic relationship. And you see that here in these two graphs, right, so the representation. So here we have one data set, so one example, where the data, so the relationship between the two variables can be very well described using a straight line, right? So it's basically a linear function can really, so describe this relationship with only minimal residuals, right? So they all lie almost perfectly on this line. However, we have a different situation here where there's sort of a curvilinear relationship between the two variables. And so, right, so the straight line is not as good of an approximation to the true shape of this relationship here. And so as you can see, so the first one here, the first correlation coefficient is always, so it's a Pearson correlation coefficient, the second one is Spearman, and the third one is a skipped correlation, so that is some adjustment. So these figures are from the paper that's also on Blackboard. So that is basically a robust correlation measure that reduces the influence of outliers, so using a multivariate outlier detection mechanism. So the important point here is so that we have for this data set here, or this example, so a correlation coefficient that is close to 0, right? So for Pearson and Spearman, so for both correlation coefficients. However, if the data shows this curvilinear relationship here. So then we see that Pearson correlation so drops quite a lot, whereas so Spearman is almost not affected. And why is that the case? So that's because so the actual order, so the ranks of the observations have not changed. Yeah, so it is basically so if yeah, let's assume that would be this weight and height example. So the so if basically the relationship between weight and height would show this curvilinear pattern, it wouldn't matter for Spearman, because as long as the monotonic relationship is true, as long as basically the order of the data points is the same for weight and for height. So Spearman will give you a perfect correlation coefficient, right? So as long as somebody who has rank, let's say, I don't know how many, right? So let's say these are 20 data points. And as long as a participant who has like rank 3 for weight and also rank 3 for height, and so the other one has rank 4 for weight and rank 4 for height, right? So even if they're basically, so the distance between the ranks is different for the two variables, it does not matter, right? So, and so that's what I mean by monotone. So that Spearman's correlation coefficient measures this monotonic trend, right? As long as there's a monotonic relationship, so it can have a perfect correlation of 1, right? So as long as the two variables agree in their ranks, yeah, even if the absolute differences are variable, right? So as long as the rank order is the same, so we are good. Okay. Drives me nuts. Okay, and then I use my mouse, so that always works. Okay. So, and in order to determine the significance of our correlation coefficient, so Spearman's error, we basically do the same thing that we did for Pearson. So if our, so basically if we are testing whether, so the sample comes from a population, whereas the assumed true correlation coefficient is unequal 0, so yeah, so smaller or larger than 0, then we do Fisher's Fisher's R to Z transformation, basically almost the same way we did it for Pearson's R. So again, the only difference is that, right, so that we are working with the ranks here, right, and not with the original raw data, with the raw values. And so this is a formula for transforming the scores, right? So RS here is just, so denotes the Spearman correlation coefficient. So that is our statistic, our correlation coefficient that we calculate from our sample. So in that we plug that into this formula, and then we get this transformed value. And this is the standard error of the sampling distribution, right, for this statistic. And then we can calculate our test statistic in the usual way, right? So this again is our sample, so the transformed value of our sample statistic. This is our population parameter here, again, transformed, right? So transformed version of our population parameter. And then we just divide by the standard error. And so the resulting value follows the Z distribution if the most of the assumptions are met. And in this case, it means that we have at least ordinal, scale, level, and so we are not dealing with serious outliers. Right. So, and in the more frequent case that we are testing for population correlation of 0, so we're basically testing whether our sample is likely or unlikely to come from a population with a true correlation of 0, we can use a t distribution, so in very much the same way as we did for Pearson correlation, right? So this is our test statistic here that follows the t distribution. So again, so this is our sample statistic, right? So RS, and so we are just multiplying with the square root from this term here, which is a reciprocal of the standard error for the test statistic. Okay, so in most cases, and we will have an example later today. So in most cases, or in many cases, the t-distribution gives a relatively good and robust approximation to the true or to the sampling distribution. However, if we have a population parameter that is larger than 0.95, so close to 1, and if you have a small sample and if our data are on an ordinal scale, then bootstrapping has a confidence interval or a significance test that is based on bootstrapping has better properties than the t-distribution. So in those cases, we may want to use bootstrapping. And I said that last week already, I would probably, so especially if we have a small sample, right, a small sample size, so I would probably always prefer to bootstrap the confidence interval and also use either bootstrapping or permutation testing for significance testing, right? So if you feel you need to calculate a correlation or if you really wanna make an inference on a correlation based on your sample data and your sample is very small, it's not necessarily the best idea. But if you feel you need to do that, I would use bootstrapping or permutation testing. We will talk about that in our tutorial today. So an alternative to Spearman's rho is Kendall's tau. And Kendall's tau is also a non-parametric measure of the associations or relationship between two variables. So like Spearman's rho, it requires that the data is at least on an ordinal scale. But it has a slightly different approach than Spearman's rho. So it is not a direct equivalent of the Pearson correlation coefficient, but it's based on the number of concordant and disconcordant pairs, so paired observations. That I will basically explain right now what that means. So let's assume you have two observations. So with observations, I always mean pairs, right? Pairs of observations from different observation units. So let's assume you have two animals, right? So animal 1 and animal 2. And so your variables that you're measuring and that you would like to determine the correlation for could be something like so a certain kind of food, right? So like a new food that the animal is eating. And so my example's always terrible. And how high they jump. please don't judge me on the quality of this example. So there's a new superfood, right? And you basically the X variable might be how many grams they're eating every day of this superfood, and then the Y variables how high they jump, so the maximum jump height. So right, so that's supposed to strengthen build their muscles. Okay, so let's say X is the right as a grams, and so Y is the height, so the jump height. And then we have right, our pair of observations for animal 1. So that would be how much grams, how much food they ate, and how high they jump. And then for second animal, right, how much food they ate and how high they jumped. And what so Kendall's tau is basically evaluating or determining is whether so these observation pairs are concordant or discordant. And they are concordant if they are in the same order with respect to each variable. So that means if animal 1 eats less of the food than animal 2, right? So if the xi here is lower than xj, yeah, so if animal 1 eats less than animal 2, then if animal 1 also doesn't jump as high as animal 2, then we would say so this pair is concordant, yeah, and the other way around. If they eat more than the other animal, and they also jump higher than the other animal, so then it would be a concordant observation. However, if one animal eats more than the other one, but it actually jumps lower, so it doesn't jump as high as the second animal, so then that would be a discordant pair, right? Or the other way around, if it would eat less than the second animal, but it would jump higher than this animal, so that would be discordant. I don't know why I always want to say discordant. So, and then there's also a situation where it's tied, right? So where the pairs are tied, and that means that so you have the same values, right? So so they eat the same amount of food, and then also jump the same, jump equally high. And so the idea is that if the two variables are closely related, then we will have more concordant than discordant observations, right? So the pairs that will be much more likely, and in the case of an ideal correlation, so if we have a perfect relationship, then all pairs will be concordant, right? So then if one animal eats more, it will also always jump higher. So if it eats more than the other animal, also always jump higher, and the other way around. And you can also have a perfect negative relationship, right? So where, so if one animal eats more than the other animal, then it will always jump lower. What is it? Jump lower? You know what I mean. So it will always jump not as high as the other one, right? So that would be a perfect negative relationship if that's true for all observations, for all observation pairs. And that is the entire logic behind Kendall's tau, right? It just looks at the difference in the number of concordant and discordant pairs, right? And so in the extreme cases, right, if we have a perfect correlation, perfect positive correlation, all pairs are concordant. And so none will be discordant. And if we have a perfect negative correlation, so all will be discordant and none will be concordant, right? So that would result in a value of -1, whereas the other case would result in a value of 1. So it's the same limits as for our like Pearson correlation coefficient, right? And same is true for Spearman, so in case I didn't explicitly mention that. So that's the idea. And in terms of sampling distribution, so the precise sampling distribution for tau cannot be characterized in terms of a common distribution, right? So we cannot use our standard normal distribution or t-distribution, but it can be calculated exactly for small samples. So that's an exact test. And that we can basically determine exactly how likely it is to get such a result. So this t-statistic, if so the underlying true correlation is 0. However, so that's tedious and also takes a long time. So that's why for larger samples, we can use an approximation. And so, right, if you have, especially if you're testing, so not only especially, but if you're testing, so the hypothesis that the true correlation is 0, so then we know that tau is approximately normally distributed with this standard error here, right? And then we can just divide the tau by the standard error estimate, and we can use the standard normal distribution to determine how likely our result is, right? And whether we want to maintain or so whether we want to keep our null hypothesis or not. So it's always hard to tell what is more appropriate, right? So whether it's more appropriate to use Spearman or so Spearman's or Kendall's tau. So often, so in many cases, Kendall can be more robust than Spearman, but it can also underestimate so your correlation. So which is also not always a good thing, right? And in general, so you probably want to use Kendall rather than Spearman if you have a small sample, if you have a bunch of tight ranks. Yeah, so if you have, for example, if you would use grades, if you have many people with A minuses, or here in this my silly mouse example, or animal lab animal example, if you have many animals that eat the same amount of food, so if you have many ties in your many tied ranks in your data, so Kendall's tau performs better than Spearman. So Spearman cannot handle ranks ties very well. And if you have a serious outliers, it's typically also better to use Kendall's tau than Spearman. So these are just guidelines, right? It always depends on a specific data set. So there is no rule that is always true. Okay, so then just very quickly, wanted to go over a few special cases for correlation coefficients. So often you're interested in determining the degree of association, right? The correlation between so a continuous variable on an interval scale and a dichotomous variable. That is particularly often the case in if you're developing a test, for example, and say a psychometric test like a personality test or an intelligence test. And the reason is that so you often, when you're developing such a test, then you're interested in how well so the response to an item, to a single item, and that is often yes, no, right? So 1 and 0, so the dichotomous variable corresponds to the overall test score, which is on an interval scale, right? So that is a continuous variable on internet scale, interval scale. So in order to do so, you use a point by serial correlation coefficient, right? I just wanted you to hear that term so that if you come across it, that you know what that means. And it's mathematically equivalent to Pearson's R when the dichotomous variable is simply assigned the two numeric values 0 and 1. Yeah, so that is a point by serial correlation, and it's used when when our dichotomous variable is a true dichotomy. Yeah, so like a coin toss, which is, I mean, you could argue for if you develop some psychometric test that so the answer to the item is actually not a true dichotomy, but that there's a continuous underlying this so this answer. So, and in this case, so when you actually have good reason to believe that so there's some so that the dichotomy, so on the second variable is artificial, so you can correct for that, and you can use the biserial correlation coefficient. So I just wanted to add, right? So examples, other examples, and this the one that I gave you was the overall test score and the response to like a particular item is the correlation between medication, right? You can say so patients, for example, on off medication and concentration skills, or the correlation between sex and weight. So assume that sex is binary, so has binary coding, so it's a dichotomous variable. So often, and that is a case where biserial correlation is most appropriate, right? So usually when we develop a test, we would use a point biserial correlation coefficient, despite the fact that we could assume that so basically that we have a continuum that underlies this response to a single item. But so what we often do occasionally in our research is that we artificially, so we do some split of a continuous variable. So we dichotomize a height, right, as tall versus short. And so, or we have something like occupational aptitude, and that is coded as 1 versus 0, right? And it's also reasonable to assume that's actually a continuum underlying this ability or aptitude. So, and in order to, so what the biserial correlation coefficient does, it's basically estimating the true Pearson correlation between the two variables if basically the second variable that has been converted into a dichotomy was continuous, right? So it's an estimate of how, because normally this, so if you have a dichotomous variable, so your correlation will always be lower in almost all cases, right? So but then if you have two continuous variables, because it's simply because you're losing information. So in the biserial correlation coefficient will correct for that. Okay, so that was just one thing that I, 1 second, I thought I had another, anyway. So another topic that we will talk about, or we will learn how to do that in our next week, that's very, very important, is the question, so that not only whether a correlation coefficient is so significantly different from 0, right? So, but also whether two correlation coefficients are significantly different from each other. In many cases, and you read that a lot in papers and articles, so people are interpreting so like different correlation coefficients, right? So it could be like a correlation coefficient for men versus women, or it could be correlation coefficients, so for different experimental conditions, right? And And occasionally, so I think that has become better in recent years, but in the past, you often saw that people either did not test at all whether these correlation coefficients were so differed really significantly from each other in terms of their size. So they were basically just interpreting the numeric differences. So if they were numerically different, so they were basically interpreting it as a real difference in the underlying population. Or they were interpreting it as a significance difference if the significance test for one, so basically if one correlation coefficient was significantly different from 0 and the other correlation coefficient was not significantly different from 0. Yeah. So, I mean, as I said, we'll talk about examples next week, but so let's go back to our example with men and women. So let's assume you are interested in the correlation between I don't know, exercise, amount of exercise and weight loss. Yeah, that's not a good example. But so let's assume we're interested in the amount of exercise and weight loss in men and women, and then we would find so that in women the correlation is 0.2 and in men it's 0.4. And so let's further assume that our correlation coefficient for men would be, so basically we would run a significance test and so that would say it's significantly different from 0, but for women would be insignificant, right? So as a result. And then so many researchers in the past, maybe not many, but so yeah, was too frequent, so said, well, so that means so that we can interpret so the difference in these two correlation coefficients, right? We can say men basically have a stronger relationship between exercise and weight loss in men than in women, but that's actually not true. Or it might not be true. You have to test that. Well, same way that you have to test whether how likely it is that the correlation coefficient is significantly different from 0. You also have to test whether two correlation coefficients differ significantly from each other. So and one being right, so the one being significantly different from 0 and the other one not, does not give you the answer to that question. All right. So and you have to differentiate when you're basically, in order to determine these differences, you have to differentiate whether it's an independent, so whether you're looking at independent samples, like in my men-women example, or at dependent samples, right? So an example for a dependent sample would be, I have, I now look only at women, and I'm interested whether so the amount of exercise and weight loss and the correlation between exercise and weight loss is different from the correlation between the food intake and weight loss, right? So these are, again, my examples are never great, but I hope you get the idea. So that would be a dependent sample, right? So because they all come from the same observation unit, so these measures. So in that, we have to differentiate between these two cases. And so for the independent samples, so this test is based on Fisher's R2Z transformation. So same what we did for so the test of a single correlation coefficient for a population where the correlation is not 0. And so for dependent sample, it relies on the t-distribution, right? So we have test statistics that can be calculated using this formula. You don't have to do that by hand. There is an R package, it's called CoCore, that does these calculations for you. And as I said, so we will talk about that next week. I just wanted to mention it here because it's really important. So please don't forget that and never make that mistake in your own research, right? So you always have to interpret the differences. Okay. So effect size, mentioned that earlier, we don't have to calculate effect sizes because R is a effect size. So you hopefully also know, we mentioned that last week, so if you calculate the square of R, so R squared, so then we get the proportion of variance that is shared by the two variables, so how much variance they explain in each other. Okay. So, and then these are the last few things that I just wanted to mention. So if you ever have to report the results of your correlation analysis in a paper, make sure to include the following information. So always report what the sample size is for each correlation. So of course, what estimator of association you used, what the R value was, what the confidence interval is, right? So that is, so the first three are, so that is mostly read that in papers, right? Confidence interval, not so often, right? Not always. Always show a scatter plot. Yeah, so for every correlation that you're reporting in your paper, especially those that you're interpreting. And so test all correlations that you explicitly or implicitly compare in your paper, right? So that's what I just mentioned. And so take the effect sizes, that means the R values and their uncertainty, yeah? So the confidence interval into account when you interpret your results. That's very important. So so these are just so a few recommendations that are more so also my personal view. So always think about, I mentioned it earlier, as I really want to compute a correlation. So especially if you have a small sample, if you're like that's very frequent, not so much in neurosciences actually, but in psychology or social sciences, you often see these giant right correlation matrices because they have like multiple variables and then they do the cross correlations. If you do that, always make sure that you correct for multiple comparisons, right? So to avoid an inflation of your type 1 error rate. And so make sure that you take into account that you take care of your outliers, right? So that you choose the appropriate methods for the calculation of the confidence intervals and the inference tests. And so be particularly careful when you use Pearson's correlation, right? So that all the assumptions have been met. Okay. That is just a general criticism on correlation coefficients. So what I didn't want to talk about today is on nominal measures of correlation. So so the textbook chapter is actually really good. So it's excellent. It's not that easy to digest. So especially this concept of an odds ratio is something that is like not super intuitive, but it's very frequently used, especially in medical research. And so if you have some time, maybe at the end of the semester, we can get back to it. But for now, I just leave it. I mean, I'll leave it on the slides are on Blackboard. You have the textbook, right? But so I simply think we should focus on regression analysis, and that remains optional, right? I just wanted to let you know it's there, and maybe if you have time at the end of the semester, we can talk about it. All right, so that was that. And then I wanted to talk about how to use R. Okay, so that we can bigger here again. All right. So I hope you have all the data sets. So in your workspace, so that you can work with me while we are going over so the analysis steps. Yeah, are you all? So just let me know whether you're all set to go or whether you need a couple of minutes to. So yeah. If somebody is not ready, then please complain now. Okay, otherwise I'll see you. All right, super. So we are using some data set that contains measures of exam stress. So that's a variable. So revision time and exam performance. So the exam stress is it's coded as anxiety here. And so the measures on all three variables range from 0 to 100. And so there's also a subject ID for each participant and gender, so which we won't use today. Okay, then so the first thing we're now, as always, we're importing our data to R, convert it into a table, and then we just take a look, right? So what we have, so we see we have 103 rows, so we have 103 cases, and we have 5 columns, so that is, these are all five variables, right? So that's the ID, so the subject code, that's revision time, exam performance, anxiety scores, and gender. And then again, so these 3 variables here are all scored from 0 to 100. Okay, so, and then keep in mind, right, so whenever, so we start with a correlation analysis, of course, so our method of choice is a Pearson correlation coefficient, just because it uses the maximum amount of information that we have in our data set, right, to estimate the associations, this linear relationship. And we don't want to lose that information. So that means if the assumptions are met, then we want to use Pearson. But that also means we have to take a look whether that's appropriate. Now we have to take a close look at our data first. So, and as always, right, so we first do some sanity checks. So we look at the data set to see whether everything looks normal and reasonable, right? So whether there are any missing cases, etc. And so we know that from last week, right? So we can use the describe functions. We just give it our data frame as an argument here. And so it lists us, or for our 5 variables. So just as a variable number, then the number of cases. We see, hooray, so no missing values. That's always nice. So we have 103 observations for each variable. So the means look all reasonable. So for revision time, it's rather low, but that is nothing. I mean, might be. I mean, we don't know anything, right, about the. So the data set of, if it was your data, of course, you could make a much better, judgment on whether these scores look reasonable to you or not. We haven't collected those data. We don't know how they were measured, so that's why it's a little bit limited, right? So, I mean, if we would get a mean of 1 here or of -3, so that would clearly show us that something is wrong, but so that is nothing that is a red flag, right? So the median also, it's yeah, so within reasonable distance to the mean, so that it all looks relatively, yeah, so okay. The maximum, so the minimum, maximum, right? The minimum for revision time is 0, maximum is 98, so basically it covers the entire scale. We see exam scores are between 2 and 100. Anxiety is also almost between 0 and 100. So that all looks reasonable, right? We also see the range here. That is, okay, and then we also, so 2 things to note is that, so the revision time here has a positive skew. Yeah, so that means that our data, so the majority of the data is concentrated on the left side, right, of the distribution, and then we have a long tail, right? So we have larger number of extreme values, so outliers in the upper tail of our distribution. So the opposite is true for anxiety, that has a negative skew, right? So basically, right? So that tells us basically that the majority of our participants here spend so probably rather less time revising, but there are a few who like spend a lot of time, right? So we have outliers but we have a few students who spend unusually long revision, so time on revision compared to the rest of the sample. And the opposite is true for anxiety, right? So here, so anxiety, so we have a few participants who have considerably lower anxiety scores than the majority of the sample. All right. And we also see that the kurtosis here for revision time and for anxiety is higher than for a normal distribution. And so that is not surprising, given that the skew is deviates from normality too. So that in itself could be related to the skew, right? I mean, it both could be, basically we could have like, sorry, so the higher than normal kurtosis might be driven by the tails, right? So so it might be due to one tail only. So we have to take a look at the data and decide what the problem is. All right. Okay, if you wanted to, because we're interested in calculating the correlation, so we can just start with that, right? And in order to simply get the correlation coefficient, we can use a core function in R, right? So simply core, and we could start with so two variables. Let's say revision time and exam scores, right? So we want to know what the correlation is. Pearson is the default method, so we don't need to give it an additional argument here, but the function is able to calculate Spearman and Kendall coefficients as well, right? But we have to specify if we want to do that. So, but if we want to calculate Pearson correlation, we don't have to put another argument in here. And we see, so it's a moderately sized correlation coefficient of almost 0.4, positive correlation. So that means that so the longer students study for the exam, so the higher tend to be their scores. And we can do the same thing for all other variable pairs, right? So because we don't want to type in so that for each individual pair, right? So if we basically want to know the pairwise correlations for all three variables, we can simply pull out, so we can select these three variables from our data frame, and then we just, right, we use our pipe operator, so 2 times. So first we select, right, from our data frame. So that is basically, remember, pipe operator means that so whatever so is on the left side here of the pipe operator is a first argument to the function that follows on the right side. So here, right, so we basically have exam df as a first argument. We just don't write that here. So we select so these three columns from our data frame, and then we calculate the correlation for the three variables, right? And then we get a small correlation matrix, right? So with so where the variables are in the rows here and columns. And of course, the diagonal elements are 1 because they're revision time. That is, of course, they're identical. So we have a perfect correlation here. And then, so we already calculated the correlation for revision time and exam scores. We see that there's a strong negative relationship, between revision time and anxiety. So that means so the more anxious or more stressed out students are about the exam, so the less time they spend studying. And we also have a moderate negative relationship between anxiety and exam scores. That means the more anxious, the more stressed out they are, the lower their exam scores tend to be. Yeah, I mentioned that before. So this method, so the core function can also give us Spearman and Kendall correlation coefficients. So we do that simply by specifying the method, right? So that is what is set per default to Pearson. So if we want Spearman, we have to tell R. So here, so we get the Spearman correlation coefficients. Here is a Kendall, so the Spearman's rho and Kendall's tau. And so the most important thing is that, not surprisingly, so the non-parametric correlation coefficients are a bit lower than the absolute values than Pearson correlation, and that has something to do with the fact, right? So that we are doing it on ranks only. So we are not focusing on the degrees, the extent of the distances. So we are only so focusing on the differences between the ranks, right? Not the true values. The distances between the ranks, not the distance between the true values, the raw values. And so then for Kendall, so the scores are even smaller than for Spearman. And I mentioned that, right? So it's a typical pattern, so that we see the lowest correlation coefficients for Kendall, and so then some medium values for Spearman and the highest values for Pearson. And that, so there's actually a question on assignment 4, where I'm asking you to think a little bit about why that is. So why there are these numerical differences? I have a few hints here in the assignment that should trigger some thoughts. So don't want to mention too much right now, because as I said, so that will be part of your assignment. I want you to spend the time on thinking about it. As I said, I'm happy to answer questions, but so right now we don't need to dwell on it. Okay, so so that is simply to calculate the correlation coefficients, right? So that doesn't tell us anything. So we cannot make any inferences to population, so we also cannot calculate confidence intervals from that alone, right? So and so calculating the correlation coefficients we can always do, right? There's no problem with that, no matter how skewed our data are or non-normal they are. So I mean, we can always calculate the correlation coefficient, right? So what we cannot do is, so we cannot make without any further assumptions. So we cannot make inferences to the underlying population, right? Or we have to choose the right method to make those inferences. So that's my point. Okay. So, and if you're using Pearson's correlation coefficient, right, and we want to test whether so our data comes from a population that either has a parameter that is not zero, that is substantially different from zero, then we use the Fisher R to Z transformation, right, and rely on the standard normal distribution, or otherwise if we test whether it's significantly different from zero, so whether it comes actually from a population with a true correlation coefficient of zero, then we use a t-distribution, right, to make this inference to determine whether our sample statistic is a likely or unlikely outcome if we would sample from such a population. So, but then we also have to meet the assumptions so that have to be given for the sampling distribution to be either a standard normal distribution or a t-distribution. And so, and these assumptions are mentioned that before, right? So bivariate normality. And so we also have to make sure that the relationship is actually linear. And we have to make sure that we're not dealing with excessive outliers in our data set. Okay. And a good starting point, if we are so looking at correlations or so in general, so relationship between variables, right? If you, the same is true for regression, all sorts of regression analysis, right? So correlation, regression, etc. So in general, right? So we are looking at linear models with continuous variables. So we want to do a scatter plot to see how the or a general data pattern looks like. No, it's always a good thing to do. And so here we start with a scatter plot for revision time and exam performance. All right, so and so we have one for anxiety and revision time, and also for anxiety and exam scores. So let's focus on this first scatter plot first. And there are several things that we notice when we look at the scatter plot. So, so the most interesting thing is, and that was already indicated by the descriptive statistics, is that so most or the majority of our participants have revision times under 50. I mean, whatever the 50 here means, right? So it's the vast majority of the sample is actually in the lower range of revision time. We have only a relatively few participants who study a lot. And that is not true, as you can see, it's not true for the exam scores, right? So the exam scores are spread across the entire range here relatively evenly. So that is one thing that we note, right, from the scatter plot. And another thing that's unusual is that here, right, so we don't have any data points in this area here. So that means basically none of our participants have high revision time, so basically study a lot, but have low exam scores. So that does not happen, right? So we generally see that so longer revision times go along with higher exam scores. However, for the lower revision time, right? So for this part here of our data, for the lower, right? So if they spend less time studying, so we see that there's a lot of variability in the exam scores. And that's a bit unusual pattern, right? So that, so my guess here would be, or what that generally indicates, is that there is not like a simple linear relationship between the two variables. So my assumption would be, if I would see a data set like that, again, so it's not my data, I'm not sure how they, right? So they're lacking some information that is really important. But so I would assume there's some third variable that actually determines what the relationship between revision time and exam performance looks like. So, and I'm making a guess here. So it could be something like skill level, right? So that we, so in the sense that we could say, well, revision time actually has only a positive or clear positive relationship with exam scores for students with a relatively lower skill level, whereas those who have a high skill level don't need to study much to have high exam scores, right? So that would explain why in this lower portion here of the of the distribution for revision time, we still have participants who do really well on the exam, right? So that could be, these here could be so right, if we, so this cloud here, so this quadrant, that could be students with relatively high skill levels. Just a guess. That could be complete nonsense, right? But and that is called a moderator variable. So in this case, the skill level would be a moderator. So it moderates the relationship between study time and exam scores, right? Because depending on what the value of the moderator variable is, so the relationship changes. And in this case, there would be no relationship for high skill levels and a positive relationship for lower skill levels. Again, just to give you an idea. Does it make sense?
Yes.
Yep.
Yes.
Yep. Mm-hmm.
Yeah, it does.
So then the next plot is shows the relationship between revision time and anxiety, or the data pattern for these two variables. And we see the same thing, right? So that for revision time, so we have a relatively few students who spend a lot of time on studying. And so for anxiety, we have the opposite. So we have basically, actually the majority of all students have score really high on anxiety, and there are relatively few who score, let's say, below 60, right? So and that is right. So that basically for revision time, we have seen that here already, and for anxiety, right, that corresponds to the negative. Sorry. So we have a negative skew for, right, so that corresponds to the negative skew that we saw for anxiety, right? So we have a few low, so basically a few extreme values, so a few outliers that have really low anxiety scores, but the majority is clustered in the, basically in the upper, right, so in the higher range of anxiety. And the opposite is true for revision time. But it is just a reflection of so what we see, right? So they both skewed, but in different directions. And what we see here is a trend of a, so there seems to be like a negative relationship. We also saw that in the correlation coefficients, so such that, so the higher, so the anxiety scores, the less time people spend on studying for the exam. And we also see that there are a few outliers. So this very claiming that, right, that we don't need we don't need a test to tell that there's an outlier. All I say here could be like suspicious case 2, right, for an outlier here. So that might be an outlier, but that is, these are not so clear, right? So there, but this is here a very clear outlier. Okay, this perhaps too, perhaps this. But all right, and so this is both, right? This is a bivariate and a univariate outlier. So we also remember, right? We're differentiating between univariate outliers. So univariate outliers are just points that are distant and from the other values on one variable, right? So for example, for revision time, right? So this would be these, right? All that are over 50. So these are all outliers that have these super high revision time scores. And for anxiety, right? So this would be an outlier, but also this. So all that have low anxiety scores, all participants. Then the bivariate outliers, these are the ones that are so that when you see this envelope here that is basically around them. Yeah, so let's just assume we missed some points here. I mean, you can sort of see a pattern like this. So then these are the points that are distant from this envelope, right? So that around the cloud, and very clearly, so this point is very different from the rest of all other observations. And it's hard to tell here, right? So these are probably outliers too. Okay, so, and then this is basically just a reverse pattern. So from what we have seen here in this plot, right? So just anxiety has sort of like different polarity. So that's why we see a similar overall pattern, just in a different direction. Okay. Instead of like doing the individual plots and like using ggplot and repeatedly calling so these the function, you could basically actually also use something very simple, which is just it's good. So it's called pairs. That's a pairs function, and it comes with the R. I think it comes with the R base package. And so you can just basically put the your three variables here as an argument. So give it as an argument to pairs, and then it shows you these nice scatter plots here. And that just basically it's enough, right? You can be lazy and make life much easier for you. And right, so then so this would be revision time and exam anxiety. So this plot that would be right. That it always shows what is plotted on the y-axis, and that would be on the revise would be on the y-axis, exam here would be on the x-axis, and the other way around for this one here. So it shows you the same data, right? But it's very easy. So only you have to type only one line. So okay. So
Unger,
yeah.
can you do that with other things, like on the assignment when you ask us to make a bunch of different plots? Can you do that with those as well?
Oh, you mean whether you can use a pairs function?
Yeah.
So, but this is still only one plot. This counts as one plot only. So if that's what you mean, but yeah, you can use pairs if you want to do a scatter plot. You can also use you can also use a plotting function from the R. I don't force you to use ggplot, so I just encourage you to use it because even so if I haven't done it in a while, I also have to look it up again. So the syntax. So because ggplot simply makes much better plots, and it's good to practice it. And if you're using it a lot, you get used to it. You don't have to think about it anymore. So it's actually pretty easy, and it's so much more. It gives you so much more flexibility and things you can do. So that's why I encourage it. But if you use the plotting functions from the base package, unless I explicitly say use ggplot, then it's fine. Yeah, you can use that.
Okay, thank you.
All right. So, all right. So let's look into the outlier issue a little bit closer, right? So especially, so let's check whether there are any clear univariate outliers. And in order to detect univariate outliers, always good to do a box plot. Yeah, and so we do that here. So we do our box plots. So first, we are converting our data into long format. And actually, I realized that what I used to use was a function called gather, so to do that conversion, but it's basically it's outdated. So the new function is pivot, so pivot longer, and there's also one wider if you want to go from long to wide, and it's actually much easier. So syntax is easier, so that's really cool. So if you want to do this conversion, I even like it better than the reshape package functions. So that comes from tidyverse. So I would basically that's just something that I just learned. So I didn't know that either. So pivot longer and pivot wider, right? So convert from long format from wide to long, that's longer, and then from long to wide, that's the wider version. Okay, and so this is just I tell it so what columns here I want to convert, right? Not the entire data set, so cool. And it's doing that for me, right? And so this just shows you here, that shows the first few values of what the new data frame looks like, right? So now I have, so still the subject code and the gender, right? That is unchanged. And then, so here in name, so that is basically the name of the variables that I changed into long format, right? So it's a revision time, exam scores, and anxiety, right? So these are the ones that basically were converted from wide to long. And these are the corresponding values, right? So again, so wide to long was rather than having so exam anxiety, so exam scores and revision time and anxiety in different columns. So we are basically, they're now stacked on top of each other, right? And we have an extra column so that tells us what it is. And then all the values are in this one column. It's called value. You can give that whatever name you want to, right? So you could, of course, the function also has the option to give it an argument that tells that, where you tell R, so to give that whatever name you wanted to give, and to give that another name, so this variable. All right, and then we can do a box plot. So the reason why it's nice to convert it into long format is because box plot, otherwise it's not, because they were all on the same scale. So I can plot it into one diagram, makes my life a little bit easier. And also boxplot doesn't want to have one, so boxplot always wants you to specify the x-axis for, in the aesthetics here. That means if you want to do a boxplot for a single variable, so it will complain if you give it only the y value. So you have to specify the x here. If you basically, so what you can do is if you don't have, if you really want to do a box plot for a single variable only, you can just say x equals, and then either two, what is it called, the quotes. So two quotation marks with no space in between, so just empty. Or you can just give it some name. You could say, you can call it, I don't know what, variable or whatever, right? And so just a string and quotation marks to say x equals whatever name you want to be printed here, right? And then R will be happy. So ggplot will be happy, but it wants you to specify the x value, so the x aesthetic. So it does not accept nothing. So histogram does, right? But for this, it does not work for box plot. Interesting. So, all right. So, and just as a reminder, right? So box plots are pretty cool. So they have a lot of information. I just want to remind you of repeating things. So this is a median, right? So this is the box is the interquartile range. That's the 25th percentile. That's the 75th percentile. Here is the highest value that's not an outlier. This is the lowest value is not an outlier, right? Outlier is 1.5 times the interquartile range from the 25th percentile downwards and the 75th percentile upwards. And so all these circles here, or these dots, are considered outliers, right? And that is consistent with all the other things that we have been looking at so far, so that they're outliers for anxiety. So exam scores look pretty like symmetric, and so these are, right, so outliers in the lower tail, and here outliers in the upper tail, right? So there are only very few people who have low exam anxiety scores, and relatively few people with high revision times. So basically just confirms. So this, I don't want to spend too much time on this. It's just really, really helpful if you want to know what actually the values, what are the values here. So right, you see that, but you actually want to know if it's your data set and you want to work with it, you want to know, so first, what are the values and what are the case numbers? So what is a row in the data set, right? So because you may want to transform them, you may want to exclude them, you may want to take a closer look at them. So you want to know where can I find these values in my data set, right? Where are they and what are they? So, and you can do that using so the boxplot.stats, and then basically you create this object, and then your access of this in this object as a field out, and so you're accessing that, right? So and then it prints all the values for you that are considered outliers. And so this is, so it uses the which function. It's also very, very helpful to extract the row numbers that correspond to these outliers. So that means the case numbers, right? So that's where you actually have these outlying values. It's just for you if you want to actually use that in your own data analysis later. All right, so right, and then we can go back to the specific rows and find them in our data set. Okay, so of course we can also identify outliers on percentiles, right? So here that would be, so that tells us what values are in the basically lowest 2.5% and the highest 97.5%. It's not that meaningful in this case because we know the data is skewed, so basically cutting off on both sides doesn't make too much sense, but I just wanted to show you, right, how you would do it on this, based on this percentile method that we talked about in theory in class. So you have it all in here. And so, all right, so then just very quickly, because I want to move on to different things, is so if you want to check our normality assumption, right? So then we always want to plot our histograms. And so again, right, no big surprise here. We see the positive skew, so the right skew for revision time. We see that exam scores are relatively normal. It's funny, so there's so they're like so there. I think it has to do with the method that they use to calculate the exam scores, probably with a number of points. So certain values are simply not possible here. That also means that the bin width is not ideal. So I should have selected that differently because it's finer. The bin width is finer than actually differentiation of my scores here. But I didn't bother, so. But so you probably want to choose a different bin size. All right. So then so the left, the negative skew for exam anxiety, right? So these are our QQ plots, and that is, so what I'm using here is actually a modified package that is pretty cool. So wait a second, did somebody, I can't, at the moment I don't see the chat. So if you have questions, so please just unmute yourself. Okay. So just wanted to bring that to your attention. So there's a package that's called QQplot. And that makes so QQplots even a cooler feature of so that we can have all sorts of nice things. For example, these confidence bands here around your right, so around this expected line. So if you would have a normal distribution, so and this confidence band, right, so that helps you basically that you don't have to eyeball whether they're like. So how much the empirical quantiles deviate from theoretical ones, you have some like statistical threshold. But again, keep in mind, if your sample size is large, so even though they're outside, the confidence band is not necessarily a big issue, right? I mean that, yes, this, I wouldn't bother. So that is okay, right? These here, yeah, clearly, right? And so this curvilinear shape here, it's very typical, right? So that's a so for data that have it's basically a positive skew here, right? So that's our vision time. So they are always, so the empirical quantiles are always larger than the observed quantiles, right? So that is because, right, we have more, especially here in the upper and the right tail. So the observed values are, the quantiles are, so the observed values are larger than what would you expect for if that data set came from a normal distribution. So you have basically more extreme values, or more extreme, larger values than in a normal distribution, right? That is going to corresponds to this idea that you have the long right tail, right? So that goes, and so you have basically a fatter tail on the right side. Okay. Yeah, and then this is the opposite pattern here, right? So same thing, curvilinear, so, but it goes in the other direction, and that would be for negative speed, right? Alrighty, so, okay, so we can safely assume that so we have both an issue with outliers, and we have an issue with our distribution assumptions. So using so the T distribution for inferences and or confidence intervals probably not a good idea. So okay, then let us actually start. So far we have calculated correlation coefficients themselves, right? But we haven't calculated actually the test, right? So we haven't run any any significance test, right? Or we haven't tried to estimate the confidence interval. So in order to do so, you can use a function core test that comes with the psych package. So core test. And again, so you can tell so R or this function what method you want to use, whether Spearman, Kendall, or Pearson. And you can also tell it whether you want to use an alpha adjustment, so a type 1 error adjustment, and which method you want to use, right? So Bonferroni or, and so that is especially if you have like huge correlation matrices and you want to basically that method will automatically adjust your p-values, right? So you don't have to do it in an extra step. But here we're not interested in that, so that's why I said none. Okay. So, and what it gives you, it's again, so the correlation matrix here, right? So we did that at the beginning already. So you see your correlation coefficients. It tells you what the sample size is, and then it gives you the probability value. So these are just your p-values, right? So, and then for the, of course, so these are meaningless here, the diagonal. And you basically test whether the correlation between the revision time and exam anxiety is significantly different from zero, right? And then zero here just means they are super, super, super small, your p-values, right? So that's why R just prints a zero. That doesn't mean there's an error, so they're basically, they're so small, they're basically zero, right? So p-values. Okay. So, and then you can do the same thing for Kendall, and here you see, right? So the Kendall, so so basically it tells you zero whenever it's smaller than 0.001. So, and here for Kendall, again, you see what we had determined earlier already, and you see the corresponding p-values, right? And so they're also relatively small. Okay, yeah. So given the nature of this data, so I mean, I think both would. I mean, the sample size is relatively large, so you probably I see how you would choose Spearman here rather than Kendall. So I think it would be appropriate or justifiable to use both of them. I would probably rather want to be on the safer side because of the distribution assumptions and the violation of the distribution assumptions, the outlier issue. I probably would rather choose Kendall, but yeah, so it would be justifiable to use Spearman as well, probably in this case. All right, so and then in the next step here, so basically what we can do, right? So for if we have data that violates the assumptions, right? So then we have three options. We can either use our robust measures, we can use the non-parametric measures, right? So Spearman and Kendall, or we can try to do some transformation to basically transform our data and hope that this will result in a normal distribution, get rid of the outliers. Or we can use bootstrapping or permutation testing, right, to calculate our confidence intervals and make our inferences to the population, right, so that we don't have to rely on the t distribution to do that because the assumptions. So our test statistic does not follow a t distribution, right, because the assumptions for that are violated, so we cannot use that. Or our sampling distribution is different, right, and that's why we have to bootstrap it. So we have to create our own sampling distribution. Alrighty, so that is just here. It's just trying a few transformations. It's just to show you a little bit, right? To basically, because that was not part of the, I gave you the formulas, but was not really part of the last tutorial. So this is just doing it with a real data set and looking at the data, right? And so you can see that the square root transform does a pretty good job for the revision time. And so for the anxiety scores, log transform is doing a little bit better. So we have this one outlier here, which we probably want to exclude, but so that actually doesn't do too much. So it's also because the sample is relatively large, right? So a single outlier is not that much of an issue. Okay. So, all right, so and then basically what I'm doing is so after transforming the data, I'm recalculating the correlation coefficients. They change, of course, in many cases. In others, they don't. So, right, so they actually that is important. So let me go over that. So the correlation coefficients will change, of course, if we compare it with the Pearson correlation coefficient. Transforming the data, so using the square root transform or the log transform, and then comparing the Spearman and so Spearman's rho and Kendall's tau for the transform and the untransformed data, won't change the coefficients. So the reason is that these are monotonic transformations. That means they do not change the rank order. So it's for the so you will see that in the tutorial. Just don't want to go into details. In one case, we are reversing the order of our scores, right? Because we have the negative skew for anxiety. So that's why we first reverse the order of our scores, and then we do the transformation. So that's, of course, will flip that makes a negative correlation or positive correlation. But aside from that, a square root transformation for values that are larger than 0, and also the log transform is a monotonic transformation. That means if one value was larger than the other one before the transformation, it will still be larger after the transformation, the other way around. So it means the monos as a rank order. The order of the values is not changed, and because that all what counts for Kendall and Spearman. So these coefficients don't change, so they're not affected by the transformation. Pearson is, but Spearman and Kendall are not. Okay, so and then the last thing that I wanted to talk about today, where are we? Here is bootstrapping correlations. So, and that is, as I mentioned before, so that is a preferred method. So that's what we typically want to do if we have a violation of the assumptions or if we have a very small sample. And so this is just a reminder. So what is bootstrapping doing? So in bootstrapping, we have to create our own sampling distribution, right? So because we know that, so we cannot use a standard normal distribution because simply our test statistic or correlation coefficients are not normally distributed. So the transformed ones, right? So the R to Z. So we also cannot use a t-distribution because we know they do not follow t-distribution. So what we have to do is we basically have to estimate the shape of our sampling distribution. And so our best guess is we say, okay, we have our sample. We hope that it's a random sample. So if it's a random sample, we hope it will be representative of our population. So basically, we treat our sample as a mini population, and we create our sampling distribution by sampling from our sample. Right? We say, okay, so our sample is just a miniature version of the population, and now we are creating our own sampling distribution by pretending our sample is a population. We are just sampling from our sample. And then we're doing that many times. We come up with an estimate of the sampling distribution, and then we can determine, right? So the confidence interval, we know what's the standard error. We can calculate the standard error for this, right? For this empirical sampling distribution, and we can calculate confidence intervals, and we can perform a significance test based on that, right? Okay, so, and that's what we're going to do. So the only thing that's tricky, so what we're using is the boot package that also has a function that's called boot that is doing the entire bootstrapping thing. And it's not only for correlation coefficients, it's you can bootstrap every statistic, right? So you can come up with your own statistic and can use that package and you can do bootstrapping. So, so the only thing that is tricky, I'm exaggerating. There are actually many things that are a little trickier about it, but in terms of implementation for you as beginners, right? So to use R and to use programming, the tricky thing is that so you actually have to write your own function, and this function basically tells boot how to calculate the statistic. So how to calculate the sample statistic. So basically you have to tell boot, so this boot function that which does a bootstrapping for you, how to calculate Pearson's R, or how to calculate Kendall's tau, or how to calculate Spearman's rho. And it's not as hard as it sounds, because you can still use the pre-implemented functions that R has. So you can use a core function, right? So you just have to modify it a little bit, right? So, and that's what we're doing here. So here we are defining, we're specifying a function that is called getRP, so it's correlation Pearson, right? And that is the syntax for defining a function. So basically we're writing our own function now. As you can always, we have never done that before, but so you do that a lot actually when you program with R, so you can write your own functions and then later use them. Right? You are not limited to the function that R gives you. You can write your own functions. And so that is a syntax, right? So we use that keyword function. So, and then so these are basically in the parentheses here, we define the arguments, and then we have these curly brackets. And in the curly brackets, that's the body of the function, right? So that is basically what the function is doing. So that's a data manipulation, whatever, right? Transformation that we are doing. Right, so and then later when we actually use a function, so then we just can, right, so as any other function in R, we use getRP, and then we just giving it the arguments that we specify here, right? So later function calls. All right. So, and what we're defining here, so we don't even need that here, that just gives us the option to just specify so certain rows of R, or to limit the actually the selection a little bit. So, and so the important thing is here, right? So we tell R how to calculate the correlation, so Pearson's correlation coefficient, and so we can simply use the pre-implemented core function, right? So we just basically we pull the third columns or the first field from the output from core, right? And we just define the two variables, right? So the two vectors here that we have given our function in these arguments here, right? So, right, so we're basically pulling that out of our data set based on the arguments here, right? So, because we do not always want to use the entire data frame, right? But we only want to use certain columns. And so those columns are defined here, right? And then we give that here to core. All right. And then this is just a return value. So that means this function returns the correlation coefficient. All right, and then we can feed that into the boot function. So boot function comes from R, right? And the boot package. And then we give the boot function just our data set. So we tell it, right? And that is so what our variables are. So revision time and exam anxiety and exam scores, sorry, in this case. We tell it how many samples we want to draw, right? There are 1,000. And that just, you could also say 10,000 or 100,000, depends on how powerful your machine is and how long you want to wait. And then here's a statistic. So that is the function that calculates the sample statistic, right? Which is in this case is Pearson's R. And so that's what we defined here. All right. And so then we create this new object. It's called boot Pearson, and contains like right, a number of important information about the result of the bootstrapping. And so we see here it's ordinary non-parametric bootstrap, so don't have to worry about that. It just corresponds to the scheme that I explained to you, right? So what we are doing, we are sampling from our sample, this replacement, and so that we don't give it any other information that we might have about the population distribution. And so the important part here are the bootstrap statistics. So the T1 here is simply our so basically our estimated parameter. So that's a vector that contains all the sample statistics from all the 1,000 samples that we drew from our from our sample. And so the right, we already know that the correlation coefficient is 0.397. So the second value is a bias. That's just the difference between the Pearson correlation coefficient for our sample and the mean of our sampling distribution. So we see that this bias is very, very small. So that's good, right? More or less unbiased. And that is a standard error. That's just a standard deviation of the sampling distribution. So we can also plot our sampling distribution. It's cool. So we see here, right? So that is our basically our statistic, right? And these are that's the density function. So that's the distribution of all the different samples of the R's that we get from all the 1,000 samples that we collected, right? So that we drew from, right? So remember, so for bootstrapping is always sampling with replacement. Otherwise, you wouldn't get any variation because the sample size equals the sample size for the bootstrapping equals our sample size. So basically, we would always draw 103 values here. And if we would do that without replacement, then we would always have the identical sample, namely our sample, right? But if we do it with replacement, then we have different values each time. Okay, so this is a distribution of our sample means here. Looks pretty good, right? Pretty symmetric, so all nothing too concerning. So I also see that looks pretty good. Here's a QQ plot. So it's a nicely shaped sampling distribution. And then we can also access directly this confidence interval for our correlation coefficient, right? And so it will give us, actually, if we don't tell boot otherwise, it will give us a whole range, so a bunch of different estimates of a confidence interval. So the normal, the basics, the percentile, and the BCA. I have relatively a lot of text that explains that a little bit the differences between these methods. So in most cases, we don't want to use normal. So we may want to use basic. So we may want to use percentile. In most cases, we want to use BCA because that's a bias correction. So if there's a bias in our, right, so for our basically the parameter estimation from our sampling distribution. So if the mean of our sampling distribution deviates a lot from our sample mean, so then it's a biased estimator, right? So in this case, we are benefiting a lot from this coefficient. Otherwise, a percentile coefficient will also do a relatively decent job. So here we have very little to no bias. That's why they're very similar. And in general, right? So because we have such a well-behaved sampling distribution, the sampling distribution here is normal, looks all good, right? We don't have a bias, and it's not skewed. So, and all the estimators here, so all the confidence of different methods are pretty much the same. So that's good, right? It doesn't really matter. Okay. So, right, I could also define, I could change what I could do is I can change the confidence level. I can tell boot that I want only, so this, right? So the bias corrected interval. So that is all things that I can specify. And these are, right, this is a little bit extra information for you on how to choose the right method. Okay, so I'm probably going to stop here because for the sake of time, because I rather want to give you option to ask questions or to just stick your heads together to talk a little bit about assignment 4. So this, I'm doing the same thing for anxiety and revision time here. And here the sampling distribution is not quite as well behaved as before. And so that has certain implications. So we also have, we can basically what we see here is that the bootstrap confidence intervals are way different from the ones that are based on the t-distribution. And and then last but not least, I have so the bootstrap for Kendall's tau, right? So we can bootstrap, also we can bootstrap Spearman, we can bootstrap all correlation coefficients or any other statistic, right? Any other parameter. All right, so that is just FYI, so for your information. And then, so for sake of completeness, also have permutation test here. So one that comes with R in a package and one that is handwritten. So, but they're doing the same thing, but just to show you the anatomy of a permutation test here. So, and that if you don't sweat it. That is just for those of you who are interested and want to like think about a bit more advanced stuff. But it's fine. All right, so that was what I wanted to tell you about so the correlations. And so perhaps you can let me know what you want to do with, I mean, if you don't have that much time left, but are there any pressing questions regarding assignment 4, any things that were unclear, anything that you want to talk about?
I have a few questions based on the wording, just to confirm
Yeah.
that I understand what you mean.
Yeah.
So for A, I just wanted to confirm that you mean we're doing 8 histograms.
Yes.
Great. All right. And then also 8 QQ plots for B. Right?
Yeah, so for the QQ plots, I mean, there's a little bit redundancy. So if you explain it, if you explain the deviations for one plot in very much details, and you can refer to these explanations, and you don't have to write it out for each single plot again. You can basically just make it short and say, as I explained for A plot, blah, 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 as I explained for A. So that is the same thing. Right, so basically what I want you to do is for the QQ plots, I want you, so the way we were talking about how the skew looks like, right? So the positive and the negative skew, I just want to make sure you understand it. So why are they, what do I see here, right? So why is it like a, why does it look like a C lying on its back versus the other way around? So what is the relationship between the theoretical quantiles and the empirical quantiles, and what does it indicate and why? So I just want to make sure you think about it and you understand it.
Okay. And then also for C, we can just use the describe function, and then we should focus on making really good explanations for what they mean.
Yeah.
Okay.
No, the z-scores for skewness and kurtosis, they actually, I want you to basically, you have to use a stat desk probably. I mean, now you can also use describe and then do it by hand. It just, so I want you to convert them to z-scores, right? So to basically divide them by the standard error.
Okay. Then, I guess I was confused a little bit about missingness. Like that would mean like, how do we deal with missing values? Like what kinds of methods can we use to replace the missing values possibly?
Yeah, so that is
like the NA.
Yeah, basically I want
right?
you
The missing NAs. Okay.
Right, I just want you to basically, don't have to do it. I want to make sure that you that you've got the general idea. So, right, we talked about the missing at random, missing completely at random, non-missing at random. And so basically based on the data, so what would be your steps? And what would you basically, how would you check for like certain things that are relevant for choosing the right method to deal with missing values? Right, so you could either exclude, right? So you could do the list-wise deletion, so you can just exclude the cases. You can exclude variables. You could impute, and that all depends on like certain criteria that are given. And I just want you to give me like an answer what you think would be appropriate in this case and why. I don't actually want you to do it. I just want you to tell me what you would do. Just throw them out.
So
Yeah.
like we don't have to worry about the other 40 columns, 50 columns. We just worry about the NAs, etc. in the 20 columns.
Yeah. So if you would basically get that data set, what would you do?
Okay, great. Thank you. That was all my questions.
All right. Yeah, and for 3, it says appropriate method. I hope I'm clear what that means. I mean, you can that's maybe a little bit misleading. I mean, you can always calculate the correlation, but let's assume that you also, so I always assume that you also want to make inferences and calculate a confidence interval, for example. All right. Yeah, and then 3B is difficult. 3B is a little bit like really a star task. So that is hard. It's hard. I mean, you will probably get, I'm not sure, you probably won't get full points, but fractions. And so again, so if you're not 100% sure, then it's not a big deal, but at least I think about it. And again, so what I want you to do is to really think about the meaning of the correlation coefficients. Of what are they measuring? How are they basically conceptualizing a relationship? And so why does it have certain effects on the size? So what information goes into these correlation coefficients? Yeah. All right, so if there are no other questions, then I just wanted to, based on assignment 2, I just wanted to mention 2 things. So yeah, so one group did a really, really awesome job. So for assignment 2, that was fantastic. The others were also good. I mean, so actually, the grades were not that fantastic, but so it was really not right. So I think many concepts were actually well understood. So I was glad to see that. But there were 2 patterns that wait a second, I have to find it here. There were some misunderstandings. Right. Okay. So the first one is confidence interval. So what is a confidence interval? And again, so I just want to repeat that. So it's a common misconception. So the confidence interval, again, so it's a certain so if I have right, I have a sample statistic, for example, sample mean, and then I calculate a confidence interval, so around that mean, right, using the sampling distribution of the mean. So then the first thing that you always have to keep in mind, so this confidence interval is different for each sample of the same size that I draw from this population, from the same population. Well, it means if you have your sample of like 40 students and you were interested in exam anxiety today, and you calculate the mean, and then you calculate the the confidence interval for the mean, then this will be a different value than when you draw another sample of 40 students from the same population tomorrow, right? And then you do it another time, each time you're getting a different confidence interval. So, and then in each individual confidence interval, either contains the true parameter, so the true mean, or does not. Yeah, either does or does not. So the probability that this individual confidence interval contains a true parameter is either 1 or 0. Yeah, either it does or does not. And we don't know. We do not know whether it does or does not. So, and the confidence level, so what this percentage, so that is again, so that is something that is related to a long-term estimate, or if you do that, if you basically draw samples in an infinite number of times, that means in 95% of all confidence, so of all samples that you draw from this population of the same size, right? If you have the 95% confidence interval. So then 95% of these confidence intervals that are all different, right? So they're all different, they're not the same, they're all different confidence intervals. 95% of them will contain the true population parameter. That is the meaning of a confidence interval, right? So in the long run, if you do that in an infinite number of times, then you're basically, you have the 95% confidence interval. 95% of all your confidence intervals were different for each individual sample will contain the true parameter, but you don't know for a given confidence interval whether it does or does not. That being said, yeah, so it is likely, yeah, so that a confidence, if you have a 95% confidence interval and a 99 confidence interval, so it is likely since right, if I do the because yeah, 95 and 100 are like, it's actually not true, right? So, but because 95% of them, so a vast majority does contain the true parameter, it is sort of, we are willing to believe that the true population parameter is within this confidence interval that we estimated for our one sample, but we don't know. No, we never know. I hope that became a little bit more clear, but that was a bit. And then, so don't forget, right? So if we do, so the other thing was about the sampling distribution. Wait a second. Yeah, if you have a 95% confidence interval, so how many intervals do we expect to contain the true population parameter? 95%, right? Or if a 90% constant interval, then we expect 90% to contain this population parameter. So that means for, right, when you use this, the sampling, just the sampling app, then it was, something was wrong, right? Because for your 95% confidence interval, so you had a much larger percentage of intervals that did not contain the true parameter. So you had like something like 40% or so. And then many gave an answer and said, well, that's exactly what I expect. But no. We expect if we calculate it, so basically if we simulate the 95%, right? So this these intervals, then this exact percentage that we are putting in, we also want that roughly, right? Because it's not like an infinite number of times; it's just a limited number of times that we are sampling. But we want to see roughly at least the right percentage. Yeah, we want to see roughly 5% of the samples of the confidence intervals. Sorry, in 95% of the and 5% of the confidence intervals, roughly we expect not to see the true parameter in those confidence intervals. And the reason that we saw more is that, right, so it's one, the small sample size, and two, the small population proportion, right, that it was underlying, so that was assumed in this particular task. And then, so another thing that I noticed is that you were confusing the sampling size, so it's basically the sample size and how many samples we draw. So the sample size is how many observations are in one sample, right? So that means how many subjects do I draw from my population in one sample, right? And if I determine the sampling distributions, then I can draw 10,000 samples, but it doesn't mean my sample is big. That means the number of that means the number of samples so that the number of samples is large, but not the sample size. Sample size is small. And what matters for the central limit theorem is the sample size, not how many samples I draw. Yeah, it's a sample size that matters. Because the central limit theorem refers to like the an infinite number anyway. But the sample size is always how many subjects from my population in one go. How many do I take out? That's my sample size. And for the central limit theorem, that sample size has to go to basically, right? That has to increase. So these were the two things that were a little bit unclear. So if you're still having issues, so conceptualizing that, then let me know. But that is important. So I just wanted to, I hope that I was relatively so long in my feedback. I hope that helped a little bit. But if you're still confused, then let me know, tell me. Yeah.
Okay, I think that was helpful.
Okay, so anything else that you?
Are your office hours today?
Yeah, so I have actually, yeah, if you want to talk to me, so then I know that, so Patrick, I wanted to talk to you a little bit. So if you have time today, so that would be good. And if anyone else wants to talk to me, then maybe we can like put you in order so that you don't wait too long. So yeah, but I'm available until 8. Yeah, Nora, did you want to, I mean, do you think it's relatively quick or do you think it will take longer?
I think it'll take like 10 minutes.
10 minutes, all right.
And more.
Yeah, Patrick, so what would you prefer? Would you prefer that we talk now or maybe after Nora?
And Dr. Inger, I don't mind going before or after Nora. It's really,
Okay.
I'll be 10 minutes, so maybe Nora wants to go second because I know she'll be longer, but either is fine with me.
All right, so then I would say, Nora, so just if you could give me maybe 5 minutes, so then let's, so we can talk maybe at 7:01, 7:02, and then Patrick, we can talk at 7:15. Is that okay?
Sure, yeah, that's fine.
All right, super. Then I mean, you should, the others, so have a good evening. So I will just leave it open as a meeting. So I will just, I will be back. I will just mute myself and we'll be back in 5 minutes.
Thank you. Bye-bye.
All right. Bye.